Hello and welcome to the 20th session of the discussion on the machining science course, and this is the last session that we are having here. So, let me remind you that last time in our previous session we were discussing the thermal aspects of machining, and we said that because of the plastic deformation the majority of the heat is produced. Next source of heat generation is the friction between the chip and the tool along the rake face of the tool, and finally, a bit of heat is generated because of the friction between the flank face and already machined surface. Now, out of that total 100% of heat which is generated, majority of the heat, which is about 80% again, goes with the chip. Next, it goes about 20%, 15 to 20% with the tool, and the rest up to 5% remaining in the workpiece. Now, here I also discussed that measuring temperature in the cutting zone we can measure using the thermocouples, but when we measure the temperature in the machining zone, it will be the temperature of the machining zone and not the temperature in the shear plane or the temperature in the tool chip contact length or tool chip contact area. But it is very important to find out what is the average temperature in the shear plane or the average temperature in the chip tool contact length. So, there is a thermal model through which we can find out the average shear plane temperature, and if you see the slide, I will repeat once again that this is it can be measured from the rate at which the shear energy is expended along the shear plane, which is Ws is the shear energy, which is equal to Fs into Vs. So, for orthogonal cutting, due to transportation, heat is being transported. So, this is the equation we have from the thermal engineering, and this heat 80% of that or some coefficient by which this is the fraction of heat going to the chip and which is about 80%. So, the coefficient is 0.8 and this is the energy which is equal to Fs into Vs. So, from this equation we can find out the value of the average shear plane temperature, which you said is equal to this, and then we put the value of the Fs and which is from the Marchants we have said we have seen here that this is the cutting force into cos phi minus thrust force into sin phi, and the Vs which is the shear velocity, which we have also derived from the sine rule, applying the sine rule, and this is cos alpha divided by cos phi minus alpha. So, this is the expression that we are getting for the average shear plane temperature. This is the analytical way of finding out the average shear plane temperature. Next, we will discuss the final topic is the surface finish. This is, as you understand, one of the most important factors, because if the surface finish is not produced according to our requirement, the machining process is not satisfactory. And earlier we have seen that all these parameters we can control for getting a better surface finish. And as you know, the surface roughness is the opposite to the surface finish, meaning that when the surface roughness is very high, the finish is very bad, and the surface roughness is indicated by the undulations or those undulations on the surface after machining. Let us see why the surface roughness is produced on the machined surface. Particularly, the surface roughness in the produced surfaces is caused because of two reasons. One, which is the inherent geometrical configuration involved in the process. What are those inherent geometrical configuration? That means, we have a certain process, we have a certain machine tool of certain accuracy, we have certain combination of workpiece and tool material. These are the and some other things, these are the inherent geometrical configuration. That means, we cannot have much control on that, this is given to us. So, therefore, it is called the ideal roughness. So, the roughness produced because of the inherent geometrical configuration in the process, this will be known as the ideal roughness. And the second reason is due to built up edge formation, due to vibration, etc., and on which, as you understand, we have the control. We can reduce the built up edge formation, we can reduce the vibration, and this is called this source of generation or the production of the surface roughness is called the natural roughness. The total roughness will be the sum of the ideal roughness plus the natural roughness. So, here the surface roughness, now ideal roughness indicates the best possible finish that can be obtained by a given operation. What does it mean? That you cannot get better than ideal roughness, in the sense that we cannot have any control over that. So, we will have this surface roughness. So, this is the best possible finish that can be obtained. Now, let us take example of turning process, and say that turning process is performed by a single point cutting tool, which is sharp, let us say. This tool is given a feed, this is the feed direction, and the workpiece is rotated at a particular frequency. Let us say this is the rotation of the workpiece, okay, n, and for each rotation of the workpiece, the tool is moved. Now, let us say in one revolution of the workpiece, the tool has moved from this position to this position. Okay. This we have seen earlier, that this is known as the feed. Feed is given in millimeter per revolution unit. So, this is the millimeter of the movement of the tool along the feed direction per revolution of the workpiece. N is given as the RPM, this is the revolution per minute. Now, in here we have the from this point to this point, this is the depth of cut, okay, depth of cut, and this is the undulation that is being formed on the workpiece, and from here to here this will be known as the H maximum, let us say. So, H maximum is the surface roughness. So, in one word, what we are having is that within that depth of cut, all right, there is some undulation, and that undulation, let us say, from this point to this point, okay, and this is the surface roughness. So, this is the depth of cut and this is the H maximum. Now, let us see that from this point to this point, this will be the feed, and if this is the tool, sharp tool which is being used, this angle will be the side cutting edge angle and this angle will be the end cutting edge angle. Okay. Now, if we take this triangle, this small triangle, and if we exaggerate this triangle, let us say we will call it A, this point we will call it as a B, and this point we will call it as a O. So, we will take the O, B and A. This is the triangle which has been taken here. Now, in this triangle, if you see that this is the angle, this is the angle which is the gamma S, which is side cutting edge angle, and this is the angle which is gamma E, which is the end cutting edge angle. Okay. As I said that the end cutting edge angle is this, so this will be the end cutting edge angle, and this will be the side cutting edge angle if you put a normal to the OB from the A. So, from A we have taken a normal as it has been shown here. So, let us say on the OB. Okay. So, let us call that as AN, all right. So, the surface roughness value can be found out from this triangle by saying that AN is the equivalent to this, okay, or AN is the value of the surface roughness, okay, and OB is the feed value, and the angles are side cutting edge angle and the end cutting edge angle. From this triangle, what we can say is that if this is equal to, this is the feed, this is equal to OB, okay, OB is equal to BN plus ON, all right, BN plus ON. Now, if we say the cos of the gamma S, this will be equal to no sorry, let us take tan of gamma s. Okay. So, tan of gamma s, this will be equal to B n divided by A n, okay, B n divided by A n. So, therefore, A n, which is the h of the tan of gamma s is equal to B n. Okay. And similarly, if we take the tan of gamma e, this will be equal to A n divided by what? This one, O n. Okay. So, cot gamma e, this will be O n by A n, and A n into cot gamma e. A n, we have seen that this is h. So, h cot gamma e will be the A n. So, h we can find out from this equation, because f is equal to B n plus O n, this is B n, all right, we found out here, and this is O n that we found out from here. And here from this equation you take h common, and the h is equal to f divided by tan gamma s plus cot gamma e. Now, this is important because here we know that if we are having the turning process with a sharp tool, then this is how we can control the surface roughness, because we know that the surface roughness basically depend on the feed, okay, because these are inherent. We have a particular tool that we have selected, where we have the gamma s and gamma e which is fixed, which are fixed. Okay. Now, let us see that if we have a round nose or the nose radius, then how this process getting affected. Let us say if the tool used is not sharp now, okay, but suppose it has a nose radius and is a small nose radius, let us say this is the nose radius, this is the value of the nose radius r, okay, everywhere it is r. Now, this is the workpiece, and we have the tool which is being fed. So, it has been fed from this position to this position in one revolution of the workpiece, and so therefore, this is the value from here to here, which is the feed, right, that is we have already said. The same value is coming in the next revolution of the workpiece. So, this is the f. Now, if we take this and exaggerate it, all right, now the h, that will be the undulation or the surface roughness will be here. This is what is shown here, that h is from the peak to valley, it is called. This is the peak, this is the valley, and this is the distance that will indicate the surface roughness. So, in here O and this from O, this is the center of the tool, let us say nose radius. O is indicating the r, which is the nose radius of the tool. This is the intersection, and we take a normal here. So, from this triangle, this is r, which is the nose radius, all right, and from here to here it is f, that is feed, equivalent to this as I have shown it. So, therefore, this can be assumed to be feed by 2, f by 2, and from this equation what we can get is that r square, OB square is equal to OA square plus AB square. So, r is OB is r equal to f square by 4, because AB is f by 2, AB square is f square by 4, divided by OA square, and OA square is nothing but O and this is r minus this, which is h. So, r minus h square. From this equation you can find out that since h is very small, so h can be almost equal to 0. So, then if you open it up, it will be like this, h square you ignore, and you will have the value of the h, which is the surface roughness, which will be equal to f square by 8 r. Now, you find out or you estimate by comparing the two values, that is h is equal to this, which is in the case of the sharp tool, and this is the value which is in the case of the tool with the nose radius. You will find that the surface finish or the roughness in the case of the tool with the nose radius, roughness will be less, that means surface finish will be better. Okay. And here it is mostly dependent on the f square, all right. And of course, you can see that it is inversely proportional to r. Next, let us say that during milling what happens. Now, earlier if you remember, I said that in case of milling, here it is the feed taken as the feed per tooth. That means, in milling cutter there are more than one tooth. So, obviously, there will be 6, 8, 12, okay. And the movement of the tool in one revolution of the workpiece, movement of the chip of the tooth, that is given by the feed, which is called the feed per tooth. So, here it is written F is equal to feed per cutting tooth. So, feed is advance per tooth here. Okay. Now, in case of single point cutting tool, it is the feed is the movement of the cutting tool, that is the, because there is only single point. So, here each tooth is considered to be a single point tool in case of milling cutter. So, advancement per tooth of the milling cutter is considered to be the feed in milling. Now, if you see that this is one position of the milling cutter, okay. This is one position of the milling cutter, and because of the feed given here. So, let us say this is the Vf, okay, feed velocity, and this is the Vc, which is the velocity given to the milling cutter. So, because of that, it has moved from this position to this position, and therefore, this is the position, this is the distance, that is the advancement per tooth, and therefore, this is considered to be the feed. Now, if we again join this is the center of the milling cutter, you join this intersection, okay, and from here to here it is the feed. So, therefore, from this value to this point, it will be d by f by 2, that is from this point to this point, all right. Now, O A, this can be considered as O to this point, this is, let us say we will call it as C, I will take the pen. Now, let us say this point we will call as C, okay. So, O A can be considered as O C minus C A, O C minus C A. Now, O C, this is wrongly shown as H, I am sorry, please correct it, that H is actually from peak to valley, as I said. So, from here to here, this is the value of H. So, value of H will be AC, if you see. So, AC or CA, this is H, okay. OC is the d by 2, therefore, OA, this is OC is d by 2 minus H, okay. This is what it is written here, d by 2 minus H. AB is f by 2, as I said. So, from this triangle, OB square is equal to AB square plus OA square, OB is d by 2, OA is f by 2, and AB, as we said, is d2 minus H, sorry, OA is d2 minus H, AB is f by 2, okay, AB is f by 2, this one, and OA is the d by 2 minus H. So, if you solve this equation, obviously, now you ignore that because H is very small, and by ignoring that, f square by 4 is equal to d H, this is the equation that we will be getting, and therefore, the H value, that is the surface roughness, it will be equal to f square divided by 4 into d, and f, as we said, is equal to V f divided by N z. In case of milling, it is the feed per tooth, which is equal to the feed velocity divided by the rotational speed RPM of the milling cutter multiplied by the Z, which is the number of teeth in the milling cutter. Okay. So, therefore, in the F, if we put the Vf by Nz, so you will find that H is equal to Vf square divided by 4 dN square and the Z square. Now, if we look into this equation carefully, you can actually say that we have few parameters here which can be manipulated to get the minimum roughness. Okay. And amongst these, basically that is the VF and the N, because D is the diameter of the milling cutter which is fixed. You have selected a particular milling cutter and that milling cutter will have particular number of teeth. So, therefore, you can decrease the value of the VF or you can increase the value of the N. So, to decrease the H. But now, if we change the value of the VF, the MRR will be affected or the production rate will be affected, because MRR, if you remember, it is the area into velocity. Okay. So, in that case VF should not be changed, because we do not want the power or the production capacity to be changed. So, therefore, if you only parameter which is left is the RPM of the milling cutter, and by changing the RPM of the milling cutter you can actually change the surface roughness or the surface finish during the milling process. This is the basic idea behind this, to discuss that what is the parameter or what are the parameters on which we can have the control to manipulate or to improve the surface finish of the surface during the milling process. So, this analytically we can see that these are the two parameters, but VF cannot be changed, because by changing the VF, once again I am repeating, it will, the MRR, material removal rate, and the production rate will be changed, and we can change only the N, which is the RPM of the milling cutter. Okay. Now, let us see what happens in case of grinding. So, before we do that, let us conclude that we can change the H, as I said, by either changing feed or speed. You can see this. So, here it is written that power will be changed, because MRR is given where we have the VF involved. So, that we have already said. Now, there is a small example, numerical example, you can see that the VF is given, diameter is given, Z is given, this number of teeth, RPM is given, and you can find out from here the what is the value of the H. So, if you compare, why this example I have given, because you have to compare that with the similar parametric value of the turning or milling. You can see that in turning, the surface roughness that you are getting, that or surface finish that you are getting, this is in milling it is better, in turning the roughness will be more. So, because you can see that 1.56 into 10 to the power minus 8, these are the very practical values, and for these values you will have a very small value of the surface roughness. So, this is in millimeter, because here we are taking all this in millimeter. Okay. So, this you can convert into micron, and you can find out that this is still very less. Let us see what happens in case of grinding. This is a schematic diagram of the path that the grinding wheel is going through. As the feed is given, that is the VF is given, let us say we have the grinding wheel, let us say this is the grinding wheel. Okay. This is the earlier position of that grinding wheel, and this is the earlier position of the another position of the grinding wheel. So, these are the centers of the grinding wheel, all right. So, therefore, the workpiece that we will be getting will be something like this, and on this workpiece the VF is given, that is the feed velocity. So, because of the feed velocity and the cutting velocity which is imparted on the grinding wheel, there will be a movement from this point to this point, from this point to this point, which we earlier said equivalent to, in case of milling for example, is the feed per tooth, or in case of turning it is the feed. So, here let us see what happens. If there are C number of cutting points per unit area on the wheel surface and the average chip has width B, then the distance between two successive points, which we can call as the grain spacing on the wheel surface, this will be 1 by B into C. Okay. So, I would like to remind you that we have earlier seen a chip, okay, in grinding, and this was represented in this way, you remember that. So, in this we have this as a B max, we said this is the maximum width, and this value was the T1 max. Okay. So, we are saying that if the chip has the width let us say b, okay, and the number of C is the number of cutting points per unit area on the wheel. This is otherwise called the grain concentration, which is C. Now, then the distance between the two successive points on the wheel surface will be 1 by b into C. Okay. This distance 1 by BC is on the grinding wheel. The same distance when it is translated on the workpiece, this is the workpiece, okay. This will be equal to the Vf upon Vc times that, because on the workpiece it will be depending on what will be the ratio of the feed velocity and the cutting velocity, because due to that it is moving on the workpiece. Okay. So, therefore, the corresponding distance on the workpiece surface will be Vf by Vc times the distance between the two successive points, which is 1 by Bc. Now, this distance we will call as the SF on the workpiece, that is the distance moved by through the successive grains on the workpiece. So, this SF can be given therefore as Vf by Vc times C into B max, okay, C into B max here. So, B max as I showed it here. Of course, the Vf is the work speed, that is the feed velocity given, work speed is this. So, gamma g, that is the wheel grinding wheel ratio, we said that this is B max divided by half of T1 max. So, from here B max you can find out, put the value of the B max here, this value, and you will get the SF is equal to this. Okay. So, keep it like this. Now, from this triangle you can find out that OA square is equal to AB square plus OB square. Now, AB is the SF by 2 and OB is equal to O, and let us say this is again this point is N. So, ON minus NB, and the NB is the H, okay, from here to this is H. So, therefore, OB will be ON, which is the D by 2 minus H, like we have done in case of milling. So, we are writing it like this, that this square D by 2 square, okay, plus this square is equal to AB square. So, from here we can find out that SF, which is this, is equal to 2 over DH, all right. D is the grinding wheel diameter. So, therefore, you equalize them because this also SF value, and you will find out that SF is equal to 2 root over DH if you solve this equation, that this is equal to 2 root over DH. From here we can find out that since we have the T1 maximum, if you find out that this was here, then from here you find out what is the Vf divided by Vc into gamma g, segregate that, put it in here, and finally what you are getting is that the H value is 225. Well, do not bother about this value because this is a constant, and then we can say that the H this is proportional to T1 square divided by D. This is important to know because then we can find out that if we have to improve the surface finish in the grinding process, we actually have to manipulate the T1, which is the uncut thickness. That is the importance of finding out the T1 maximum. You remember how scrupulously we found out the T1 maximum. So, this is also another point that importance of the T1. It shows that we can manipulate the T1, which is the uncut thickness. In case of grinding, it is the T1 average that is taken, which is half of T1 maximum, and that actually can be regulated to improve the surface finish of the grinding process. Overall, this is what I wanted to tell you during the 20 sessions of our discussion in the on the course on machining science. I hope you have enjoyed. If you have any question, then we can discuss it in the forum. Thank you for your attention.